So now we're going to look into multi-cores, which is a trend that you may take for given, but it's something that for all people like myself is a fairly recent development in the computer history. It looks like an obvious step to take. It used to be that computers were big and bulky. Maybe it required several circuit boards to implement a single CPU. Then you managed to squeeze a CPU into a single circuit board. You managed to put a CPU into a single chip called the microprocessor. Big revolution, Eureka, we've got it, we've done it. But now with multi-cores, it looks like a logic step. Instead of putting just one CPU into chip, why don't you put many CPUs into chip? But it was actually a big deal. This move is a big revolution, and it's not done because the software vendors or the operating system people or any customers actually want this to happen. It was a step that was necessary to take because of technology. And that's what which is the first thing that we're going to discuss here. Why did the multi-core revolution happen? And we're going to look at some of the performance bottlenecks of multi-cores, some commercial offerings, and then some reflections where multi-core is heading in the future. So why is it happening, or why was everybody doing it pretty much at the same time? So up until 2007, pretty much nobody did multi-cores. A few companies, few very specialized chips had more than one CPU on a chip. But then 2006, 2007, suddenly everybody was forced to do it. And what really happened then was that it became impossible to make single core implementations run faster or come up with a chip that had larger throughput than the previous generation. So the development, that the nice Moore's law curve, it had already started to trickle off a little bit even before this point in time. But in 2007 we hit the wall, and we hit it hard. And the only way you could produce chips that had better performance, for some definition of performance, was to go to multi-core. And there were, in my book, 3 reasons for why that happened. The first reason was that right in this curve, the popularly called Moore's law curve on a log scale, we were able to stay on this for 2 reasons. One was that we increased the frequency of the chips between each generation because the transistors got smaller, but also because we were getting better and better at exploring instruction level parallelism. So we introduced the out of order executions and the branch predictions and the superscalar pipelines and the all those things were introduced here, and for each of these feature we were better and better at finding instruction level parallelism, scheduling more and more parallel work on instructions in our pipeline, and that was one way to increase performance. But at that point in time, we already played all the obvious tricks in the book, and making a reorder buffer which was 10 times larger was not going to give you 10 times more performance. So we were running out of innovative ideas here. Another reason why this multi-core revolution may have happened, and this was a paper that was published in like 2001 that made the case that when you shrink the transistors, every time you have a new technology and you shrink the transistors, you also shrink the wires connecting the transistors on the silicon scale. And when you shrink the transistor, its resistance goes up. And when the resistance goes up, the signal propagation delay also goes up. So the time it takes to communicate between transistors went up for every generation, every time you shrank their technology, while the speed of the transistors went down. And we started to come to a point in time now when the signal propagation delay started to dominate. Well, there are solutions around that. You can, for example, for long traveling signals that are important for your design, you could use a wider feature, so this reason may not have hit as hard as people were predicting, but it still was a substantial reason why we started to look into multi-cores. Because if you have multiple cores on a chip, and then you don't have to travel so far on the silicon. Let's say I have 4 cores. That means that there is not so much interaction between the 4 cores, so signal only has to travel a quarter as far on the die. The largest reason though for going to multi-core was power consumption. So we're going to discuss this in the next couple of slides. So power consumption, or the dynamic power consumption, is proportional roughly to the capacitance of the chip, the frequency at which it operates, and the voltage that we supply to the chip. So here you have again. So here's the equation for dynamic power: capacitance times frequency times voltage squared. And this capacitance is actually roughly proportional to the area of the chip, because if you assume the whole area is covered by the same ratio of wires and transistors, then it's a linear scale between capacitance and how much area you have on your chip. So that's roughly area times frequency times voltage. And this was actually a big deal. So looking at this, how these different parameters fitted together right around when multi-cores happened, people from Freescale, they make power processors, from the embedded power processors, they made an experiment. So they took one of the chips that was designed to run at a specific frequency, and they overclocked that, like some of you probably do at home when you want to beat somebody else in some computer game. You overclock your processor and you manage to get some better performance out of it. Well, that's what these engineers did. They overclocked the processor by 20%. So here is compared to the nominal, what you would normally get on the processor if you ran it at the normal frequency. So by running it 20% faster, they got some speed up. So, but not proportional to it, because the memory didn't get faster, and we know that memory is a big deal. So maybe they got, in their example, they got a 13% speed up, but the power went up with 50%. So what happened here? So they increased the frequency by 20%, but this whole power equation increased by 50%. So what happened here is, in order for you to run at a higher frequency, you also have to increase the voltage. And increasing the voltage even a little bit is a big deal, because it's voltage squared. So that's why the power consumption went up a big deal. Instead, if you're conscious about power, what you should do is to run your CPU slightly slower when what it is designed to do, because if you run it slower, well, you're not going to see a proportional slower speed of the machine, because once more, memory is a big deal. It's not just the CPU, and the power consumption is going to be much lower. For the same reason the power consumption was much higher here, you're going to see a much lower drop here. So in their experiment, lowering the frequency to 80% of nominal frequency gave you a power consumption of roughly half. So then they made the experiment. Well, what if we add twice the amount of hardware? So back then, the multi-cores didn't exist. So they took 2 CPU chips, ran them together at 80% of the frequency. So what you see here is, that if you have a linear scaling of your application, this is the performance you can get of your application. And the power consumption is roughly the same as if you ran one CPU at the nominal frequency. So this is sort of the motivation of what happened here. And especially around the time when multi-cores happened, you saw these kind of effects of scaling. And this is something which is sometimes referred to as dynamic voltage frequency scaling. So if you lower the voltage and the frequency at the same time, so it's rather you lower the frequency, and thanks to that you can lower your voltage, and thanks to this equation, that is a big deal. So today, however, the DVFS effects are smaller than what you see in this picture, because voltage does not vary as much with the frequency as it used to. It varies a little bit, so you're going to get a little bit of advantage here, but you're roughly going to see that you change the frequency, the voltage stays pretty much the same. Still, that could be a good idea if you have lots of slack in your application. If your CPU is standing waiting for DRAM a lot anyhow, lowering the frequency is not going to hurt the performance that much, but will still save pretty much linear or slightly better than linear performance properties linear with the frequency. So that's DVFS. Okay, so we talked a lot about dynamic energy in the previous slides. So what is the dynamic energy proportional to? Frequency squared, voltage squared, or capacitance squared? So it's voltage squared. And DVFS is a technique to help you save energy. So how does it save energy? Lower voltage and higher frequency, lower voltage and lower frequency, higher voltage, higher frequency, higher voltage, lower frequency. So it's the second choice, lower voltage, lower frequency. So I'm going to talk about an effect called Dennard scaling, and this is very important for the introduction of multicores. So if you look at this equation here and you look at how these different components are affected when you go to a new technology, technology with the transistors and the wires are smaller, you will get roughly a constant area. So if you look at the chips, the size of the chips that Intel makes, doesn't change that much over generation, pretty much the same area for the same segment of the market, because that is economics that tells you that that's the kind of cost that that part of the market can handle. So that doesn't change that much. So C will not change that much in the equation. Frequency can potentially increase with smaller transistors, and that's what's happened before the multi-core revolution happened. Every generation you crank the frequency up, 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 and that's where you did get the majority of your performance improvement from, even though we computer architect also would like to take a little bit of credit. It was mostly the technology people that gave us the great performance. And up till that point in time, thanks to some insight that a person called Robert Dennard had from IBM, you were also able to lower the voltage for every generation. And the increase in frequency and the effect that the lower voltage square had pretty much cancel each other out. So we saw for every time you released a new CPU, it roughly had the same power consumption. Well, maybe it went up a little bit, but not anything dramatic. However, this trend has stopped. So what's called the Dennard scaling, which is the fact that you can lower the voltage for smaller transistors, is a trend that has stopped. So when they go between generations now, the chips pretty much has the same voltage, and that means that you cannot increase the frequency because they're already at a power consumption which is close to the limit of what each respective segment of the market can handle. So that they are the voltage, the energy that the server market can handle, the desktop can handle, and so on. So increasing the frequency, since we didn't get any help from Dennard anymore, increasing the frequency is not an option. So now the frequency has gone pretty flat over the last 5 or 7 years or so. Just as a side remark, Robert Dennard is a pretty amazing person. He's one of those little circuit nerds that figures out how to build transistors that you often don't hear much about. You hear much about people like Steve Jobs and the people who are in the media and who are the big people to the outside. But Robert Dennard, well, this is of course was an important property that he managed to formulate, the Dennard scaling, which took us so far with the frequency scaling. He also in the 60s made another small observation or invention, and that invention is called dynamic RAM. So that dynamic RAM, DRAM, is another invention by Robert Dennard. Okay, so if you can't increase the frequency, what are the options? Are we going to tell the customers that, guess what, you're going to buy these new chips, smaller transistors, but they don't run any faster? Well, I don't think so. So we have to find a way of improving the performance, and that's what's going to come riding on a white horse helping us is transaction level, thread level parallelism, TLP, as we discussed earlier when we talked about coherence. So what you're going to see here in this generation between processors is, yes, we are going to do multi-cores or chip multiprocessors, as they were called early on, before it, because this. So the writing has been on the wall in computer architecture for a long, long time. So we were writing papers about how to make chip multiprocessors many, many years before the first multi-core came around. And then for commercial reasons, they couldn't take our word, chip multiprocessor, so they made up their own word, multi-cores. So this is simply just a multiprocessor on a chip. The big thing that happened here, though, was that this a tremendous paradigm shift. Up until this point in time, the goal of any architect when they get up in the morning was to make a single thread run faster. The world had lots of single-threaded programs that fitted into that model. However, after the multi-core revolution, when a computer architect gets out of bed in the morning, he asks himself, how can I make a parallel application run faster? So after this point in time, then we require the application writer or the compiler, if they can, to tease some kind of thread-level parallelism out of the application. If they can't do that, then their application will not run any faster. And that was a big deal, big change in computer history.